Yeah, then let's talk a little bit more about this advection diffusion equation combination in the context of heat transfer, because this will relate to this week's exercise. You guys remember last week when we were dealing with our introduction to thermal chronology that we were talking about dating things that have something to do with temperature. And for instance, time since rock was at some temperature in the earth. And of course, when you want to start then looking at interpreting the ages from thermal chronology, oftentimes you'll need to use some kind of thermal model to do that. And that's what we're going to do in this week's exercise, is essentially play around with the advection diffusion equation to look at how temperature varies with depth in the earth. And then when we come back in weeks 6 and 7, we'll actually bring that into predicting thermal chronometer ages, which I think is kind of a nice combination of things we've done in the course. But for today, our focus is going to be on just the advection diffusion equation applied to heat transfer. And yeah, we'll start just with a little bit of terminology and then show some basic concepts of heat transfer that reflects the processes of erosion and sedimentation and how they affect temperature with depth in the earth. So as far as thermal chronology goes, last week we saw in the exercise this Dodson's equation that allows you to kind of predict what a closure temperature should be. And essentially what thermal chronometers can record is cooling. So as rocks go from deeper in the earth up toward the surface, they'll record the time since they were at this effective closure temperature. And usually you're collecting your samples at or near the Earth's surface. So you have the duration it took in terms of time to go from depth to the surface. And they can record exhumation. So this is essentially the process by which rock goes from deep in the earth up to the surface, which is usually driven by things like erosion. So rivers and glaciers and landslides and things like that remove rock from the surface and expose rock beneath the surface. But it can also be tectonic exhumation. If you have a normal fault, just the motion of the fault itself can take rock that was below the Earth's surface and bring it up to be exposed at the surface. And so thermal chronometers record both of these things, and they're usually quite closely connected. I have one slide here that's from a kind of old paper now, but just defines some of these different terms in case you're curious. At the time, there was a kind of tendency that scientists were using these three terms, exhumation, denudation, and erosion, kind of interchangeably, but each of them do have proper definitions. And probably the biggest thing for us is to consider is exhumation, because that's the process that's going to get rocks from depth to the surface, where, for instance, a thermal chronometer age could be calculated for some exposed bedrock. So again, the details of the terms here aren't necessarily that important for the purposes of our exercise this week, but the terms are here in case you're interested. And exhumation is the thing that we're mostly focused on in this case. And the tendency with exhumation is that it results in upward advection of rock. So if you have some geological process, could be a river flowing across the Earth's surface or a glacier that's basically scraping the surface clean, removing rock and overburden from the surface and exposing rock beneath it, the effective process that you see is upward transport of mass toward the Earth's surface. So this exhumation process results in rock that's at relatively warm temperatures deeper in the Earth, moving up toward the surface and cooling down. And this is the reason why this little stick figure says erosion hot, is that essentially the process of erosion is removing the mass and bringing things up toward the surface. And usually, as far as the process goes, if it's happening at more than about 1/10 of a millimeter per year, it's important to consider in your temperature calculation. So there's a lot of places where exhumation rates are slower than 1/10 of a millimeter per year. I'd say pretty much almost everywhere in Finland this would be the case. Rates of bedrock erosion are extremely slow here because there's not that much sort of topography. There's probably some places where there's steeper parts of rivers where you might have a little bit like locally faster rates of exhumation, but it's slowly exhuming for the most part in these kind of cratonic settings. But most mountainous places, you're going to have rates of exhumation that are faster, maybe on the order of a few millimeters per year, bringing mass up toward the Earth's surface. And notably, if you're aware of things like the rates of glacial isostatic adjustment, those rates can be higher. But the thing is that you're not really exhuming the rock, you're just moving the Earth's surface up. So, the amount of erosion that you have when you're rebounding from the past ice age is relatively small. So you could basically have rocks that are sitting near the surface that are moving up at even a centimeter per year, for instance, in parts of western Finland. But the rates of exhumation are typically still really slower than that. So, so that's exhumation. And if we want to simulate this or calculate the effects of exhumation in heat transfer equation, it looks like this. The reason this looks a lot nastier than what we saw in the solution before is the fact that this is now including time. And when you include time into this heat transfer equation, it gets a little bit messier. So you end up with a first term here that has a initial temperature gradient that you assume, and then you've got some depth plus the velocity of advection, advection velocity times how much time has passed, and then another kind of term here that has these things like this complementary error function in there. That is one of the terms you've got to deal with. There's some exponential terms in here, and as you can see, it's just a generally more complicated mathematical relationship when you include time. And this is still in one dimension. This is still assuming constant things like the thermal diffusivity is constant everywhere in the model where you're doing a calculation. And so if you start having things like changes in diffusivity for different rock types or whatever, you can't even use this. You have to use a sort of numerical approach to solve the advection diffusion equation because there is no direct calculation you can do. But this will be our pet, or one of our pet equations for this week's exercise. So you get a chance to convert this nasty looking thing into a Python function that you can use then to calculate the variation in temperature with depth and time in the Earth's crust. So luckily for you, you don't have to worry about like coming up with a way to calculate the complementary error function. We can use a function out of the SciPy library. So that will save you a bit of time. If you have to do that by hand, it's a little bit more tricky. But in essence, what you see, for instance, with erosion is if we look at a plot like this of a geotherm, so this is just showing from like over 10 kilometers depth in the crust, the temperature along some line that starts initially going from the surface perhaps down to 250 degrees. What you can see with erosion and as a result of exhumation and moving warm rocks up toward the surface with time is that the temperature gradient will increase over time while this exhumation process is taking place. And so if you start out at 0 million years here, after 15 million years, the temperature would have increased to follow the line that is here. And for instance, at the base at 10 kilometers depth, in this case, in this model, your temperature would have gone from 250 degrees or so up to something more like 430 or something like that. I don't know actually what the value is there, but you can see that it's increased significantly. This is using that same equation that we just saw here. And in that particular solution, there is nothing that fixes the temperature at the bottom of the crust. So it's allowed to continue to increase in the way that the equation has been solved. Sedimentation, in contrast, is basically the opposite thing. It's advection, but in the opposite direction. So in that case, you're depositing rock at the surface and burying things. So essentially, you're pushing the crust down with time as you accumulate sediment, which means that This process, if you start with the same initial temperature going from 0 to 250 degrees in a 10-kilometer thick part of the crust, and you have this sedimentation process active with a millimeter per year, after 15 million years, the temperatures drop to something like 125 degrees because you're basically just piling on cold sediment at the surface and pushing the pile of rock down with time. At 1 millimeter per year, in this case, that's the equivalent to 10 kilometers per million years in terms of a rate. So essentially here, I think it's 0 million years, 5, 10, and 15. So already here, after the 10 million years of sedimentation, basically this would all be sediment from the surface down to the depth here, and your temperature would have dropped to 150 degrees from the initial 250. So process works more or less the same with the opposite effect. If you have erosion, you heat up. If you have sedimentation, you cool the crust down. And you can look at this maybe visually, for instance here, that if we calculate what the temperature gradient is, so like let's imagine we go down to 2 kilometers depth here, and we say, okay, the surface temperature is 0 degrees. The temperature at 2 kilometers depth, if we just follow it down here, is something like 50. And then what you'd come up with that in terms of a temperature gradient is if you take the 50 degrees temperature difference between here and the surface, divide that by 2 kilometers, and you get 25 degrees C per kilometer for the starting kind of initial temperatures that we're using here. In this case, after 15 million years, if you go to that same 2 kilometer depth, the temperature is something more like 100 degrees. So then you take your 100 degrees, divide by 2 kilometers, and you end up with a temperature gradient that's twice as high, 50 degrees C per kilometer. And that gives you some sense that the temperature gradient does increase quite significantly, especially shallower in the model over time, as this exhumation process is taking place. And then there's a couple figures in here that are maybe, I don't know, a bit more challenging to understand, but along the horizontal axis here, this is erosion duration. So this is how long the exhumation process has been going on. The different lines here are representing the rate of exhumation. So you can see here for number of years, this is 10 to the 6, so 1 million years there. This would be 100 million years for 10 to the 8. And this is the temperature gradient. And initially it was 25 degrees because it was basically going from 0 to 250 over 10 kilometer thick crust. That's 25 degrees C per kilometer. If the rate of exhumation is 0.01 millimeters per year, essentially you see that temperature gradient doesn't change over time, which means that this advection process is too slow to matter. Every time you move some warm rock up toward the surface, the heat is conducted away so quickly that the temperature never really rises. However, if the rate goes up, so if you go to 1 millimeter per year, you can see that after a million years, you're already starting to have increases in the temperature gradient, and those would continue to increase with time using this particular temperature calculation. And you see that same thing for 10 millimeters a year, that the sort of temperature gradient will rapidly increase after even something like 1,000 years. It's starting to increase in that scenario. So the faster the advection velocity is, the sooner and the faster the temperature gradient will increase. And of course, for sedimentation, just the opposite's true. So this is just the kind of corresponding plot to the one that's above for sedimentation. And I guess this is just actually the sedimentation cases here, but this is just a different way to represent the same information in now at 4 kilometers depth, showing the same kind of temperature increase with time. So the point here was introducing a little bit about the ideas of this exhumation and sedimentation, how they affect temperatures in the Earth's crust, which is something we'll play with in this week's exercise, because you're going to be doing, first off, making some functions to calculate the steady state temperature in the crust and the how the temperature changes with time in the crust. You'll make functions for both of those things, and then I'm going to give you some suggested exhumation rates that you can play with to see how much the temperature varies depending on this rate of exhumation. Once you have your function, if you want to play around with different exhumation rates or sedimentation rates, you can certainly do that to get a better sense of how this works. But in principle, you could pretty much reproduce these plots if you'd like to, just to show how temperature changes with time for these different types of erosional processes or sedimentation processes. I think that's kind of it for the introductory lecture stuff. Are there any questions? Has anybody taken like the geothermics course or something where you would have seen, I'm guessing you would have seen erosion and sedimentation and how they affect crustal temperatures? Or have you seen it in other geophysics courses, for instance? Maybe not. Okay. Well, this used to be something I think that Ilmo was teaching in the geothermics course, but I think it's been a couple years since he's taught that one, so maybe it's just, yeah. Maybe enough time has gone now that that no one else is actually introducing these crustal thermal processes things, but
This made a lot of sense.
good. Okay. All right. Well, that's good. At least, yeah, some feedback is helpful. All right. So our next thing is going to be to have a look at the exercise. But why don't we take a 5-minute break now? That way we can come back fresh and have a look at the exercise and yeah, continue from there. So see you in 5 minutes.